Hello everyone, I'm Clément Gaspard, a PhD student in the Rhoban research team at the University of Bordeaux and the Library. Today, I'll be presenting FootstepNet, a method for fast online bipedal footstep planning and forecasting. In the state of the art, on humanoid locomotion, several challenges arise. The first aspect is that humanoid locomotion is a highly challenging subject due to the complexity arising from its under-actuation and high degrees of freedom. Furthermore, while footstep planning methods exist that rely on traditional search-based algorithms like A* to address this problem, they are computationally expensive. The fact that they rely on handcrafted parameters and discrete action sets also limits their flexibility. In contrast to existing research, our goal is to develop a method that designs an efficient footstep planning method for humanoid robots to navigate in local environments with obstacles, focuses on generating a minimal sequence of footsteps with a low computation time while ensuring feasibility, improves real-time performance for online applications in embedded systems, and aims for heuristic-free approaches to improve performance. The contributions of FootstepNet were then that we advance the state of humanoid locomotion control by providing a modular and versatile solution compared to end-to-end architectures. We also propose an efficient footstep planning method using deep reinforcement learning, introducing an heuristic-free approach operating in continuous action space, and achieve low computational requirements suitable for online inference. We developed a forecasting method using the critic networks to estimate the number of steps needed to reach a desired target. And finally, we validate our method through simulation and real-world deployment on a kid-sized humanoid robot during RoboCup 2023. Let's now introduce FootstepNet. FootstepNet is a deep reinforcement learning-based method trained to predict a minimal sequence of footsteps to reach a given target while avoiding a local obstacle. It employs an actor-critic algorithm, specifically TD3 in our case, to train an actor network pi and a critic network q by interacting with a geometry-based simulated environment. The actor network selects the optimal actions while the critic network evaluates these actions, providing feedback to guide the learning process. This example demonstrates the use of FootstepNet in a locomotion task. The goal is for the robot to reach a target located outside its immediate or local area while navigating around various obstacles. As you can see, the bipedal robot starts at the bottom left of the image, and we want him to reach the final target at the top right. To achieve this, we first compute an A* path to define an intermediate target. Next, we feed the intermediate target along with the position and size of the nearest obstacle into FootstepNet. The agent then computes and executes a sequence of steps to move towards the intermediate target. As the robot progresses, we update the intermediate target along the A* path, repeating this process in real time until the immediate target aligns with the final destination. FootstepNet is divided into two main components. The first is a footstep planner that uses the actor network. As shown in the graphic on the left, we provide the planner with the robot's current position, marked in blue, the target position in green, and the obstacle to avoid, shown in orange. The planner then generates the footsteps needed to reach the target by recursively executing the policy. This process is extremely fast, taking only a constant 45 microseconds per step on board the robot. The second component is the footsteps forecasting, powered by the critic network. It can efficiently estimate the number of footsteps required to reach a target without calculating the exact step sequence. This allows to select among different targets the one that can be reached the fastest. This forecasting process is also rapid, taking only a constant 60 microseconds per target on board the robot. As an example, let's take a robot that needs to score a goal by shooting a ball. It begins in a defined initial state, and there are three different possible target positions, each of which will result in a goal. The question is then, which target is minimizing the number of steps? Let's take again our three possible situations. Intuitively, we might assume that this third scenario will require the fewest steps, as it's the closest in terms of both position and orientation. However, this isn't as straightforward as it seems. Since the robot isn't omnidirectional, the problem is non-linear and more complex. Let's use FootstepNet forecast to estimate the number of footsteps for each situation. For the first scenario, the forecast estimates around 25 steps. For the second one, it forecasts 30 steps and the last one 28 steps, requiring just 60 microseconds of computation per possible target. Notably, the forecasting agent chose a different target than our initial intuition. We can observe the footsteps generated by the FootstepNet planner for the first scenario. As you can see, it took 24 steps to reach the target position from the initial one, with a computation time of 45 microseconds per step. That adds up to a total of 1080 microseconds. Let's now see the second scenario. It took 30 steps to reach the target, and finally for the last target, it required 28 steps. So, we can confirm that the results differ from our initial intuition. Due to the complexity of the action sequence, which involve both translation and rotation, based on the robot degrees of freedom, it is challenging to intuitively predict the minimum number of steps required. Let's also note that the total computation time to select the best target across all scenarios is 3690 microseconds. This example demonstrates that FootstepNet forecast took only 180 microseconds to select the target that minimizes the number of steps, whereas FootstepNet Planner needed 3690 microseconds to do the same, though it also calculated all the steps required for each scenario. To optimize computational time, we decided to first use FootstepNet forecasting module to quickly choose the target with the fewest steps, and in a second time, we use the Footstep Planner to generate the specific footsteps needed to reach the target. In conclusion, for this particular example, if we add the forecasting time to select the best target and the planning time to generate the footstep sequence to reach that target, it results in a total computation time of just over 1 millisecond. Let's note that during competition, we use the intermediate target approach, as shown in the earlier locomotion task video. This allows us to calculate only a fixed number of steps in advance, resulting in a shorter and predictable computation time. To summarize, the entire FootstepNet pipeline, which, let's remember, operates on board the robot, we start with one initial position and multiple possible targets. Our goal is to identify the target that minimizes the number of steps and the required sequence of footsteps to reach it. We input the information into FootstepNet, which first employs its forecasting module, powered by the Critic network. This module calculates the number of steps needed for each target and selects the optimal one. The chosen target is then sent to the actor-based planning module, which generates the precise footstep poses to reach it. Finally, these footsteps are executed on the real robot. Let's now take a closer look at the geometric environment in which the agent is trained. First, the action space is defined by the footsteps movement in terms of both translation and rotation. You can see the parameterization of this footstep movement displayed on the right side of the screen. The observation space is defined as follows, with all elements expressed in the frame of the current support foot. First, we have an indicator function to determine whether the current foot, left or right, is the target foot. Next, there's a 2D target footstep position, xt and yt, shown in green on the left diagram, followed by the target footstep orientation. We then include the obstacle position and size. For simplicity and computational efficiency, we represent obstacles as circles. If an obstacle isn't circular, we use the outer circle that encompasses it. Finally, note that the sigma operator manages symmetry. The reward function is expressed as displayed. Each step taken incurs a penalty of -1, encouraging the minimization of steps. Delta p and delta theta represent the position and orientation error. As for the observation space, we have an indicator function to check if the current state is colliding the obstacle. The weights W1 and W2 provide small shaping rewards to guide learning, especially during the early stages of training. Lastly, W3 acts as a colliding penalty. Each step taken colliding the obstacle is equivalent to taking an additional level 3 steps. The episode is truncated if the agent takes more than 50 steps, or it terminates when the target is reached within set tolerances. On the right side of the slide, you can see an example of a trained agent moving from a random initial position towards the ball we want to kick. In these videos, you can see the Sigma-Band robotic platform navigating with FootstepNet, both in our lab environment on the left and during RoboCup 2023 on the right. FootstepNet forecasting module provides an accurate estimate 95% of the time, achieving an improvement of 12 to 46 less steps between the best and the worst possible target. In our tests, Array Star took 5 to 10 seconds to potentially find a good footstep sequence versus around 1 millisecond for FootstepNet. Additionally, FootstepNet Planner consistently found an equal or shorter sequence 99% of the time, reducing the number of steps by an average of 14% compared to Array Star. While 14% fewer steps might seem modest, in a competition setting, every excessive computation time and every extra step can be decisive for victory. To conclude, FootstepNet is an efficient diurnal footstep planning and forecasting method for bipedal robots navigation in environments with obstacles.